So now it's time for us to move beyond sentential logic and into the domain of modern 20th century logic. This new logic is called first order logic. It's sometimes called the predicate calculus, or maybe even on occasion quantification theory or polyadic quantification theory. So the big difference and the core innovation that's going to distinguish what happened before and what we're about to study is the function of these quantifier words. So the quantifier words are words like all and some. And we've seen a whole bunch of ways that we can recombine specific declarative sentences using the logical operators to form new sentences and how we can analyze that structure. But now what we're going to do is get inside the declarative sentence itself and look for the internal logic that's due to the role of words like all and some. So, for example, if we have a sentence like all frogs are amphibians, in the way we were treating sentences and declarative sentences in sentential logic, we might label a sentence like that, a declarative sentence like that, as F. And we might join it together with F or C, where C might be, for example, Harry is a Martian. Okay. So the trouble with doing this is that we lose some of the internal structure, some of the logically relevant internal structure of F. Specifically, I can legitimately move from a sentence like this that talks about all frogs being amphibians to another sentence like this. Some frogs are amphibians. Okay, so the move from this sentence to this sentence happens because of the internal structure of the all frogs claim. So when we move from all frogs are amphibians to some frogs are amphibians, clearly this is a valid inference from here to here. Clearly it's a valid inference. The trouble is we don't have a way in sentential logic to represent this pattern of valid inference. Okay. So we need to get inside the declarative sentence to get at the way the quantifiers contribute to how we can make judgments validly. So let's see. Let's take a look at two sentences that one of which is valid, one of which is clearly invalid. And the validity and invalidity has to do with the character of the quantifiers. So here's the invalid one, and we can intuitively see, I think, that there's something wrong with this. If I say Bjorn has the flu, therefore all students have the flu, this inference is not licensed by the premises, right? So the move from Bjorn having the flu to everyone having the flu is illegitimate. By contrast, here's a perfectly valid one. All students will pass the class. Since Jan is in the class, Jan will pass the class. Now what we're going to try to do is capture what it is about those patterns of reasoning, or what it is about the internal structure of those sentences that allows us to say that the first is valid, the second is invalid. Okay, so why can't, well, let's see. So, as we'll see, there are certain patterns of reasoning, like this one, for example, that are legitimate, valid patterns of reasoning that don't get caught by sentential logic. So, for example, if I know that all whales are mammals and that at least one whale has a blowhole, it makes sense for me to conclude that at least one mammal has a blowhole. So what I'm getting at, or what we see here, is the internal structure of these sentences is playing the critical role in the judgment. Okay. And that is something that we just couldn't capture, except in some very artificial and elaborate way using sentential logic. And I don't think you could even do it then. So this was motivated by an interest in what we now call the problem of multiple generality. Philosophers and logicians in the 19th century were realizing that large parts of mathematical reasoning, for example involving the calculus, weren't easily captured within sentential logic. So mathematicians reason with multiple generality all the time. So the interplay between all and some is critically important and already in play in large branches of mathematics in the 19th century, and is crucial for many of the important advances in mathematics. There was a philosopher slash logician slash mathematician named Gottlob Frege who allowed us, using the formalism that we're going to introduce now, allowed us a way to capture or at least express some of this reasoning formally. So again, just one more example. If we have something in ordinary language like the following, we can see that there's sort of embedded logical structure that the declarative sentence as a whole can't get at. So when we say that some teacher is respected by every student, you can legitimately unpack the internal structure of that in such a way that you can conclude that all students respect at least one teacher. Okay, and that again is a valid argument. It's a valid piece of reasoning that our sentential logic misses. So what we're going to do for the next couple of clips, or for the next 3 more clips, is now that we've seen that we need to get at the internal structure of the declarative sentences, and we've touched a little bit on the history, we're going to need to introduce the formalism. We'll start talking about how we set up the formalism, how we interpret the quantifiers, how we just lay out these formal statements. I'll talk about multi-placed predicates. We'll talk about predicates, what predicates are, what the quantifiers look like, what they do, etc. And we'll talk about some of the syntax of well-formed formulas for first-order logic. Once that's out of the way, then we'll move on to some of the rules for manipulating these formulas in first-order logic. So the 2 major innovations that we'll be looking at are quantifier negation and instantiation. So I'll explain what those are as we go forward, and we'll talk a little bit about that. Along the way, we'll see how the quantifiers are interdefinable. They can be understood in terms of one another. And then finally, we'll talk about the tree rules, and we'll talk about how we run proofs for first-order logic. So that's what's on the agenda for the next 3 videos.